Hello, my name is Joshua Ferrer. I'm taking Physics 2211 at Georgia Tech, and this is my lab video. This lab discusses the change of position and motion of an object, and its relation to the motion of a falling object. So the lab discusses four key topics. The first being Newton's second law, which states that an object's acceleration is dependent on the net force being applied to a ball and the mass of that ball. Velocity is the function of speed, which uses meters per second as its units. Drag is air resistance, or how much air or another medium that an object is traveling through pushes back on that object. In this case, it's air resistance, which is pushing upward. And gravity, of course, is a universal constant that pulls all objects towards a mass, in this case, Earth. So the purpose of this lab was to use an object and demonstrate the before mentioned constant velocity, Newton's second law, and outside forces acting on an object in both a lab and a real world setting. In this lab particular, we're going to be examining drag and gravity on a ball falling. So on the right, we have five equations. The first being Newton's second law, F equals ma. The second being the updated velocity formula. The third being the updated position formula. The fourth being the force of gravity, as you see, negative mass times gravity. And the fifth being the proportion of B. We're going to be using that later in our computational model. On the left, we have a diagram of drag force and gravity acting on an object. As you see, the first model has the ball being released from rest, so only gravity is acting on it. The second has the ball mid-drop. So right now gravity is still stronger, but drag force is starting to act on it. And the last model has gravity and drag force being equal, which means that it's at terminal velocity when air resistance and gravity are at the same thing, and the ball neither speeds up or slows down anymore. Now, what you're seeing is the first part of the actual lab, the experiment of me dropping the ball. I recorded it in Tracker, and as you see, as the ball is dropping, on the right, there is a graph which has a downward sloping trend, which is what's expected as the position goes downwards in a negative direction as time increases. And moving on to my computational model, I created it in Python using glow scripts. And as you see, the initial conditions of the model, I set the mass of the ball to 0.1 to more closely match the mass of a small hollow bouncing ball. I set the original position of the ball to 0, 0, 0, and the initial velocity of the ball to 0, negative 1, 0. So the first computational model that I decided to create was just using gravity. With the formulas I mentioned before on the purpose slide, I used the updated velocity formula, as you see here, and the updated position formula. In addition to that, I calculated the net force using this long algorithm, but essentially, the net force in the situation calculates both components or vectors, in this case, only gravity. Next up, I made another computational model, this time using both gravity and drag, and the code itself is basically the same except I calculated B. I calculated B using the formula from the first slide, and this essentially adds on air resistance to the model itself. So here is the graph, finally, that we're here. I use all the computational models and experimental data, and I put them into one graph. Now, as you see, the motion of gravity and drag and motion of gravity only are pretty similar to each other, but they vary quite heavily from the experimental value, which is the blue line. This is likely due to me messing up in Tracker. In order to get the data from Tracker, I have to click as the ball is falling, and I probably mess up with my clicking, which is also why this graph does have a small curve here going upwards. That's not supposed to happen. So this is probably why the gravity and drag is so heavily different from the actual experimental value. So here are the extension questions. What does it mean? Which models, if any, predict a terminal velocity? Of a model which shows terminal velocity is obviously the model with both drag, force, and gravity. So of a second computational model. This is due to the description I gave earlier on the purpose slide. And what if? Imagine that the object was initially thrown downward. Would a terminal velocity in this case be the same or different? It wouldn't matter, as terminal velocity is only determined when gravity and drag are equal. So the computer model would be flipped. Uh, the curve would simply be going up as the computer model's slope is position in time, so the slope is velocity. So yes, it would be going up, but the terminal velocity itself would be the same. So thank you for your time.